going to town hall afterwards.
Give me just a second. All right, I'll be right back, and I think we should be good to go.
What are you looking for?
Huh?
What are you looking for?
I'm not looking for anything anymore. Okay. Let's see. So just before we begin, I just wanted to mention there's some O'Reilly stuff in the back. If you want it, please take it. I don't want to carry it with me ever again. So there's some books and stuff. And as you know, this is like our second to last meeting before we are done with part 2. So we'll have this meeting today, and then next week Ian is coming back for the chapter 12. We will then take a 2-week break, so like 2 Mondays off, and we start on August 28th with the part 3. Hopefully it's going to be here. The reason why we're waiting 2 weeks is because the fall semester needs to begin, and they just don't know what's going to happen with the rooms. So it looks like we're going to get a room, but they cannot confirm anything until all the classes are scheduled and they know for the fact what's going on. I know some of you got an email from me about leaving a review for the group. The reason being is that in the unlikely event that this is somehow going to fall through and we'll need to find a new space, I would want to be able to say we have very happy people who love it and show up, so please give us a space. So that's really my thought process. Yeah. And give me just 1 second. Yep. Take it away.
Okay. So this is a nice compact chapter. I'll be going over it twice. First I'll go through the slides, and then I'll go through the chapter, and I think all of this will fit under an hour. So the slides are pretty good. Just follow the official slides here. So several times during the chapter, Ian refers to the particular application, which is the Street View house number pipeline, which is something I worked with him on the Street View team. So I'll start by just going over that particular application so that it makes sense.
Just FYI, we don't see any slides right now.
Where did they go?
I think it's the connection is bad. Remember, it was bad last time too. And if you want to, you can use this guy right here. Maybe, so maybe this port I think maybe messed up. But you have to.
I see. Oh, cool. Okay, so this chapter is about practical applications, and I'll go over one particular application that we solved with deep learning. So the situation we had in Street View is that Street View imagery, it has a large number of images like this, which have house numbers. And originally there is a team of human operators in India who just go through all of those images and they try to find the numbers and they type them in. So when you use Google Maps and you try to navigate to a particular address, the data for the house numbers comes from there. So over time, they've worked and they've collected a large number of these examples. So the question was, can we replace these human operators with a machine so we can give them something more interesting to do? So this is actually the kind of setup which is the most ideally suited for the current deep learning technology. It's a domain where you already have a task which is already solvable by humans and where humans have been at it for some time as to create this data set you can use to train your deep learning pipeline. So when we started with it, deep learning wasn't really that hot, so we tried to use standard OCR tools. There's this OCR engine which was used for Google Books, but it turned out it just worked very badly for text. It performed almost at random accuracy. So when somebody comes and they think about the OCR problem, there's this very standard approach to solving problems, which has been kind of taken over with deep learning where there's a new approach. So I'll describe the old approach. So the old approach, when you have a task, you tended to separate it into individual stages and you try to solve each stage. So for instance, for character recognition, you would start with an image of text and you would try to find particular ways of segmenting it. So you would try to split it into possible candidates where the letters are. And then you would try to find what's the best segmentation is, and you would tune the stage separately. And then you would try to classify. So here's an example. This is a 1 on the left, and this is a 2 on the right. And this would be another stage. So you can see here, optimizing it in separate stages, it may not necessarily work very well. And the old pipeline it used vector search, and it would combine it all together. So that is the pipeline that worked badly. The pipeline that worked well, we thought, well, what if we just take a neural network, we give it a whole image of a number, and then we tell it to predict the whole number, so that you don't have to deal with the segmentation, individual classification, and vector research. And it turned out that kind of a simple approach, it required much less engineering, and it turned out to solve this task at the human accuracy at the coverage level that was required. So later we'll talk about debugging. So here's an example. When you're actually developing your system, one thing that you're always doing is you're looking at the things, at your failures. So these are examples of the failures we saw. So for instance, here's an example. It's a 6, but the system predicted it's a 5. So when developing a machine learning system, you always have to have this two-way interaction. You have a system, and you want to make sure it's not doing something silly. So you want to look at its mistakes. And if the mistakes seem reasonable, then things are okay. If the mistakes are not reasonable, you may need to improve your architecture. So some details. So the final result was just a neural network which takes an image like this and produces a complete house number. And that let us free up workers who could do other things. So. Okay, so going to the slides, and I'll refer back to this application periodically. So 3 things. Which of these things you think answer the question? Well,
Data helps.
yeah. I guess because the first one uses words like arcane and obscure, you can guess that's not the one. So basically, vast majority of machine learning just comes down to just a couple of simple techniques that you just apply over and over and over, and having lots of data. That also helps. If you have just a tiny amount of data, actually that's when you need to go into this arcane knowledge of thousands of algorithms. If you look at people that really drove the era of MNIST down, people have gone and made some really smart tricks to go get those few extra examples specified. Right now, maybe the best examples, the best models misclassify 24 examples of MNIST. So if you want to go and misclassify 23 examples, you may need to really think hard to go there without getting extra data. So this is the example that Ian refers back. A practical task, you want to develop a pipeline, it takes an image, produces a house number. So how do you solve the task? So first of all, you have to define a way to measure the success of your system. So they say you cannot improve a system if you cannot measure it. So you have to have some kind of a metric. And this metric, it needs to be connected to the real world impact. So the ideal measure of impact is probably dollars. Ultimately, everything can be converted into dollars. In our case, we had operators which were paid $6 an hour, which were sitting and looking at these images. So essentially, if we can reduce the number of images which are sent to those operators, we're just paying for electricity, which is much cheaper. So essentially, accuracy is sort of a proxy for this true metric. So you always have to think what is the true metric and find something that approximates it. The second step is to build an end-to-end system. So one thing that's one pitfall that often happens in machine learning design is people split the solution into a pipeline and they try to optimize individual stages. And actually you can see it very well in the design of the optical character recognition pipelines. Like I mentioned before, you would split the task into stages, like for instance segmentation. And actually people got so into this individual tasks, there are actually conferences on segmentation. So they don't care about the final result of the OCR system, but they have some data sets to evaluate how well you segment the example. And in practice, it doesn't really contribute much to the overall progress. It's sort of this artificial goal people create. So the point is, it's very important to have an end-to-end system which actually solves the task at hand. Maybe badly, but as long as you have a metric to evaluate, you can iterate on the system. And then finally, you have this data-driven refinement. You just try things and see what works. So you need to decide how much effort to put into the system. Do you really care about having very high accuracy or low accuracy? If you're solving a task in robotics where you have to be very accurate, you have to be realistic ahead of time. Maybe you commit to getting lots of data and spending lots of money. And some tasks you can just don't care much about this. So here's some metrics. So accuracy is the most commonly used metric. It's not always the best metric, but something like ImageNet, you try to classify, it's really comes out quite often. The second example is coverage. So coverage is if you have a system which has a choice of either performing a classification or saying, I don't know, I give up. And then you tune the system so that it only makes a prediction for the high confidence example. Those high confidence examples are the ones covered by your system. And you may care about increasing the coverage. So in the example of the house number transcription, we had those operators, and we always could send some examples to the operators. So we basically tuned the system that it could take a house number, and if it was really confident it's correct, it would classify it. Otherwise, it would send it to the operators. And here the coverage is the thing which correlated with the money, essentially, because the more examples the system chose to process, so the less examples we had to pay humans to label. Then there is the common precision and recall. Precision, a common example, what is precision? So, for instance, I'm trying to detect if I'm trying to detect some kind of disease. So I take a group of people and I say, these people have this disease. Precision is a ratio of how many of those people that I picked actually do have the disease. So for instance, if I have very high precision, you look at this group of people and everybody has this disease. If only half of them have the disease, that's precision of 0.5. And if none of them have the disease, it's precision of 0. Recall is you're flipping this. Suppose I'm interested in finding everybody who has the disease. It's the ratio of how many of people who really do have the disease that I found. So if I found everybody that has the disease in my set, I have recall of 1. If I found only half of them, I have recall of a half. And if I found none, I have recall 0. So you can see that these numbers are connected. For instance, if my test selects everybody, it has recall of 1, but it has precision is not so good. Similarly, if I just select one person, which I definitely know has the disease, I have low recall, but I have high precision. And finally, amount of error. So if you're doing linear regression, you're basically measuring how closely you fit your set. So a few words about accuracy. So again, you should always keep in mind what the underlying cost is. So for instance, for Google Maps, the underlying measure is that we want a house number that's predicted correctly. So if I got one of the digits incorrect, the whole number is wrong. So one can think of two different measures of accuracy. One can count the number of digits which are correct, which is easier, but if you actually want to maximize the real world impact, you want to count the number of examples where all the digits are correct. Luckily, these measures tend to correlate, so you shouldn't think too hard about which kind of accuracy to use, but you should think some about it. Okay, so end-to-end system. So basically, you should always start with an end-to-end system, get it running, and this end-to-end system should really solve the task at hand. So for the case of house number recognition, it's a system which does the same thing that the human is doing. The humans are given images of house numbers and they type in the house number. So this is the system that you build. So you build the system that's as simple as possible, but which has room for improvement. And one may think, well, what's the simplest system? So usually the domain you're starting with, it will have some examples where people solved similar problems. So for instance, for this house number transcription problem, we looked at similar examples, and MNIST is kind of similar. So MNIST, you have handwritten characters and you recognize them. It's also images. So essentially, we just started with the MNIST architecture, and we just resized first we filtered to only have single-digit house numbers, and we resized them to 28 by 28, and we just apply standard MNIST pipelines. And then when that worked, then you can go on, and then we ended up making the architecture more complicated to support multi-digit numbers by just duplicating this network several times for each digit. So the focus here is that you always want to have something that works on a simple problem, maybe a subset of the problem, and then you just go and iteratively refine it. You either increase the reach of the system by, here you're increasing it from just recognizing single-digit house numbers to multi-digit house numbers, and in other direction you increase the accuracy by just using tricks to train better, which I'll talk about in a second. Any questions?
Yeah, that slide, we had two different things on the left and the right with different names.
We're here.
What are those referring to, the 250 million versus 500 million parameters?
So this is the architecture we ended up using. So it had a 250,000 parameters. 12 billion connections. Oh, right. So if you're using convolution, then you have more connections than you have parameters. Essentially, when you're using convolution, you are taking the same filter, and you're replicating it several times. So because it's the same filter, you're using the same parameters. But because you're replicating it, you're having those extra connections. So that's why the numbers are different. Oh, wait. 500 million parameters. Interesting. So I guess there are two different architectures. These are pretty old slides. But yeah, so one of the networks had 12 billion connections and 500 million parameters and 5 filtering layers.
Is there any significance like the separation of the digits?
Separation of the digits? What do you mean?
I guess I'm trying to understand this architecture. Like there's digit 1, 2, and 3, and then some colors. Is there anything?
Oh, I see. So the colors, it basically indicates how the encoding worked. So the output, it had, each tower had 10 output units. And essentially, the prediction, so for instance, it decided that the second digit is digit 1. So it would just make this unit active and the rest inactive.
Gotcha, okay.
So you basically have 5 softmaxes, and then because the length of the number is variable, you can introduce a special character, which means end of input. So that's what we did. We just had 11 outputs. So the first, in the 3-digit house number, the first 3 outputs would give the first 3 digits, and the 4th output would just say end of input. Make sense?
Yeah.
So how do you do any segmentation of the image?
Nope.
It's just to feed in the images and
Yep.
it identifies whether you have 1 digit or 2 or 3.
Yep. And the interesting thing is that this even worked with vertical house numbers. So it turned out when we did this, it just figured out that sometimes numbers go left to right and sometimes go top to bottom. Whereas with the traditional OCR system, the vertical or the diagonal ones, they would be a problem.
Is there any kind of intuition why? Because for these kind of tasks, I'm more familiar with like HMMs or whatever. Because it is a sequential task.
Right.
But here there is, how are we specifying any sequence information?
We're not. So here are examples. These are the kind of examples it is able to classify. And basically, my intuition is that it has several layers. It just learns the decoder inside those layers. So instead of manually encoding a decoder, you're just giving it data, and it has enough parameters to program a simple decoder, which includes a binarizer, a segmenter, and a decoder. Yeah.
Just to make sure that I'm understanding you correctly, so for example, when it sees 250, you have the one duplicate of the network that now detects that it's 2, and then you have the same network again detecting that it's 5.
I have a single network that processes the whole image, and the very last layer has 5 softmax outputs. So you have 5 softmax outputs connecting to the last fully connected layer.
Oh, okay, that makes sense.
And sorry, just to take that one step further. So if the softmax says there's, a 1 in 4 chance that there's 4 digits, and the 3/4 chance that there's 3 digits, would it provide like a probabilistic output of that 4th digit as well?
No,
Okay,
you would. This is just the simplest possible thing
gotcha.
you can think of, and it turned out to work as well as humans. So initially, when I was designing this architecture, I got some pushback from the OCR team with these exact concerns, but eventually, when I tried it, it just worked. So this is a lesson that you should always have a data-driven approach, and you just try things and see what works and work based on that. Yeah.
So when you went through your 3 steps and did error analysis, what was your process for deciding what to try next?
My process was basically making things bigger. So I would train it. You would make the window bigger around the house number. You would make the network bigger. And at some point, you would get bottlenecked by performance. It takes longer than a day to train your system. Then you start thinking about the performance aspects, and then you start scaling your system, adding more workers, so that takes more time. And once you design the next generation architecture, which trains fast enough, then you iterate again and you make it bigger. So basically, every time I added an extra layer, or I increased the size, things became better. Basically, I would run maybe 10 experiments at a time. In one experiment, I would double the number of layers. In another experiment, I would keep the number of layers, and I would double the width of each layer. And in the third experiment, I would increase the size of the input, and then I would see which one performed the best, and that would be my new baseline. And then from that, I would again have a set of experiments and try things. So later in this chapter, Ian talks about hyperparameter search, and that's one of those areas which had a lot of research, and I haven't found it very helpful, or I don't know anybody that found it very helpful in practice. One problem is with this kind of problems, you may be training things for a couple of days, so it's kind of too long to just try hundreds of experiments. Okay, so baseline. Deep learning is getting sort of hyped right now. One may think that you should always use deep learning, but actually sometimes you shouldn't use deep learning. So when shouldn't you use deep learning? So one area is when you have really good features to start with. So deep learning is sort of very good when you're dealing with perception level applications, when you have sound, images, video. But there are some traditional applications when your features are already very good, so maybe you're good enough without it. For instance, search. When people search by keywords, keywords are actually pretty informative. So if you're searching the web, just simply matching the keywords using bag of words, that is already a very strong baseline. And at Google, they're kind of finding it hard to beat the existing systems. Now, half of Google is doing machine learning, but the core of Google search is essentially keyword matching with some extra heuristics combined by hand. They're trying to change it, but it's one of those areas where a shallow model already works pretty well. And if it has, basically if your task has really bad features, if your task has lots of features and the features aren't very good, then it's really an area where you need neural networks.
So, one question on the keywords.
Mm-hmm.
So, I have been hearing some talks about the Bayesian networks.
Mm-hmm.
So, would those keyword generations be more can be done with generative networks?
Mm-hmm. Keyword generation, what do you mean?
Yeah, like I'm typing in Google, so it suggests me few few sentences that I could be talking.
Mhm.
So is that done with deep learning already?
No, it's basically, I mean, they introduced it before deep learning was a thing, so it's kind of a very old addition. And if you think about it, how many visits Google gets? Something like 1 billion visits per day. So you can simply look at what other people, queries other people did, and sort of just do a simple classification in there. Yeah, so when your features are informative, words are pretty informative, and you have lots of data, then shallow models work pretty well. Okay, so
You
yeah.
know shell model?
What?
You know shell model?
Shallow.
Shallow.
Shallow model, like naive Bayes or logistic regression. Okay, so we're talking about how to choose your baseline, your first thing that you're doing. So you first decide if you even want to use neural networks. If you're using neural networks, you can choose what kind of architecture to use. So you can have a fully connected neural network, and that's sort of a generic neural network which works for everything. For sound, for vision. For images, people typically use convolutional neural networks. However, note that convolutional neural networks are a subset of the fully connected networks. So if you have enough data and enough compute capacity, you could actually train just as well without imposing the convolutional aspect. You could just train a fully connected network on images. And I've actually seen people try to, they first train a convolutional neural network, and then they drop that assumption, and they continue training it with those starting weights as this locally connected neural network and getting further improvements. And then if you're dealing with sequences, you can use a recurrent neural network. So those tricks, the spatial structure and sequential structure, they are essentially the tricks to restrict the possible space of models, and in exchange, they require less data to get good accuracy. So here's a typical fully connected baseline you could start with. So a couple of years ago, that was state of the art. In many tasks, you use rectified linear units. The rectified linear units is really the thing, one of the things that had the neural networks take off when the ImageNet, when the Alex Trojavsky and Yaroslav came and blew the competition away in the ImageNet competition. The one really important trick they used was this using rectified linear units. So for images, essentially everybody uses them now. Batch normalization helps, Atom helps, and then if you're doing overfitting, you could add dropout.
So you're mentioning about like when you were doing the optical character recognition, you had teams traditionally doing that kind of be like, oh no, it's not going to work.
Mm-hmm.
Before Krzyzewski and his team proposed the winning model in 2012,
Mm-hmm.
or like traditional image segmentation, people also go like, oh, it's not going to work. You're crazy.
Yeah, I mean, typically a lot of the work was done around more traditional, what are they called? The image feature descriptor methods. So there's a lot of work in things like SIFT, where essentially you train an algorithm that finds all the interesting points. If you actually look in phase detection, a lot of pretty practical phase detection methods were made before deep learning, and they actually work pretty well. So they are around this finding interesting points, and then from there trying to learn this. So before deep learning, that's really what people were trying. So more recently, I'm seeing a lot of people talking about the ResNet 50. So residual network with 50 layers, that seems to be becoming this kind of a universal baseline that you can start with. It's getting pretty good performance. And it's simpler. You don't necessarily need batch normalization, and it has better performance. And then if you're dealing with sequences, there's some standard LSTM baselines you can use. Okay, so once you have the baseline, what do? You just have this small hill climbing approach. You try some ideas, and then you keep improving your model in small steps. Okay. So one thing you pay attention to, you always look at your training error and your test error graphs. So there are several kinds of graphs you can observe. Something you can often start with. So this is your time, this is your accuracy, but let's say this error. So your trained error goes like this, and it's high, and then your test error is even higher. So this is trained. So this is a common scenario where things are just not working. Second scenario I'll talk about is you're having training errors goes down, and then the test error maybe goes down and then up. This is also another common thing to observe. Okay, so when you're observing this scenario, this is known as underfitting. Essentially, when your training set is not classified correctly, you're basically not able to fit your data. So if you can't even get good accuracy in your training set, there is no hope in getting your test set. Whereas this scenario is known as overfitting. You're able to fit your data correctly, however, you fit it well in the training set, but your model is not able to generalize. And this is known as underfitting. Okay, so what do you do when you have high training? It's sort of domain specific. You just, so there are some tricks to do. One trick is you could just take your training set and reduce it, maybe even to a single example. You just throw a single example in your algorithm and you try to train to fit it. And then if you're still getting high training error, then you just try more and more things. You try to decrease learning rate, you look at the gradients, you eventually maybe make it smaller. So if you're trying to classify an image and it's just not getting classified, you can reduce your label set to 2. If it's still not getting classified, you can maybe resize it to 2 by 2. And eventually your task becomes so small that you can actually solve it by hand, and you can check where the difference is. So luckily there is a lot of well-debugged tools out there which already train correctly, so hopefully you don't have to go down this route. But if you do, that's generally the procedure. You simplify things until you can work out the math by hand and you compare it to your algorithm. So another thing that could be happening is your model could be just too small. So for instance, if you're classifying images, if you try linear regression on the ImageNet, it's not going to classify anything, so you have to add more layers, make things bigger. So a common technique, so what if you try this and your error is better, but it's still not good enough? So another technique is to look at the errors. So you look at the errors which you're training on, but you're still not able to fit. So here's an example. This was the original number, and this is the image that was fed to the neural network. So at all stages, it's important to see what is the actual image that the neural network sees. So you can see it's not able to fit it because it's been cropped too tightly. So the correct answer is 26624. So that was one of the things that we discovered in our pipeline. And then when we found this error and then increased the window, then it fixed it. We got another 10% boost. So another thing, we started adding layers. So when we had 3 layers, the accuracy was around 92.25, and then every time we added a layer, things got better.
You mean a convolutional layer or a full text layer?
Both. So we basically, in the architecture, let's see, am I describing it here? We basically had some convolutional towers, and then we had some fully connected layers. So maybe 3 convolutional layers with normalization and then 3 fully connected. So you just make 4 convolutional and 4 fully connected. But this is actually one of the experiments we would run. We would try to add some layers to the convolutional stack, and then in a separate experiment, we would try to add some layers to the fully connected stack. And then we would just see which one performed better, and then we would take that as new baseline.
Sorry, you were on that? When you say digit 1, you mean the number 1, or you mean digit in location in the first digit? When you say digit 1 like that?
So this first softmax layer, basically
Is the length of how many numbers it sees, right?
No, it's the first. Okay, in this example, yes, but in the final architecture, we didn't bother with this. We just had a softmax layer predict. The first softmax layer predicted the first digit. The second softmax layer predicted the second digit, and then we would have a separate label for no digit.
Okay. So it was a softmax after a softmax?
No, there was just several parallel softmaxes.
Oh, parallels. Okay, got it.
So they're all connected to the last fully connected layer.
Okay, that makes sense. Okay.
Wait, I have a question.
Yeah.
It's not my question. Let me read it to you.
Okay.
It's from Cosmin. He's asking, how does one deal in practice with cases where the data has different distribution for labels in training versus test data?
When the training data and test data are different, right?
Where data has different distribution for labels, yes,
Right.
into sets.
Well, ideally, you're never in this situation. A lot of machine learning algorithms are designed with this IID assumption, independent and identically distributed. However, when you are in this assumption, the ways of dealing with this are the same as the ways of dealing with overfitting. And I will go over overfitting later. Yeah.
On that last slide, was the convolutional part the part that's doing the digit recognition, and the fully connected part is the part that's figuring out sort of which digit it is?
Unfortunately, we don't have the tools to answer this question. It does something, but I can't tell what it does. So this is one of those issues that people in neural networks are facing. For instance, in Europe, they are planning to pass this law called right to explain. When a company makes some decisions which impact users, they have to be able to explain why they made this decision. However, if you have a neural network that made the decision, we don't know why. The answer will be because we multiplied by a matrix which gave this answer in the end.
Like, say, when you're designing the convolutional part, do you try to make it so that it's big enough to at least, cover one digit by the time it gets to the top?
I see. So in this case, we didn't design it like that. The convolutional layers were standard size, like 5 by 5 or 7 by 7. It does make sense to think about these issues if you want to make the method more data efficient and pre-train. So one of the experiments we tried was to train a neural network. For instance, what if you wanted to recognize MNIST numbers where there was more than one number? You may think about training to classify a single number and somehow reusing that architecture. And if you do this, you can actually take this network and use this whole network as this multi-layer convolution. And in this case, you can think of this network being this deep convolutional filter and then adding some layers on top. However, in this case, our convolutions were too small to contain a single number. Also, there is a very high variability in the sizes. So there's some numbers which would be maybe 50 pixels wide, and some numbers would be 3 pixels wide. And we did not add any structure to reuse the knowledge across the scales. There's some research where people talk about scale invariant networks, where you train a neural network on a number that's 50 by 50 and be able to reuse the same network on a number that's 5 by 5. In our case, we had a simple architecture which didn't have any of those assumptions. And the thing is, if you have enough data, essentially, and enough capacity, essentially, the network can learn those things.
I have a question.
Yeah.
Let me read it to you. Are there some successful use cases of deep learning application on a limited data?
Unlimited data?
Mm-hmm. Limited.
Unlimited data.
Mm-hmm.
Well, all data is limited in a sense. Limited. Oh, so
Like,
limited. I guess limited in a sense.
Little data.
Small.
Yeah.
Well, MNIST is a good example. MNIST, state of the art. It's only 60,000 examples, and using convolutions, you can use neural network and train to pretty good accuracy. So when you have limited data, you really have to think and incorporate extra assumptions in your neural network. In the case of images, you really have to use convolutions. If you don't use convolutions, the 60,000 examples will give you pretty bad accuracy. If you have a lot of examples, then you could do a fully connected network, which gets good accuracy. Okay, so what we're talking about? We're talking about dealing with cases that arise in real life. So I talked about case when your training error is high. You basically have to make sure there are no bugs in your system, and you have to make sure that the examples you're giving to your system are actually possible to solve. And you have to make sure that your neural network is big enough. Now, what happens if you have high test error? So it's this scenario. So if you're having high test error, you use standard tricks to avoid overfitting. So the state-of-the-art example for MNIST is actually using data set augmentation using elastic distortions. So essentially, they're taking an image like this, and then they're trying to distort it in many ways, and they're feeding those as more examples to the data set. So actually, one of the most successful applications of this was one of the first successful applications of GPUs for training neural networks was from Schmidt-Huber's group, where they took a MNIST data set, they added these elastic distortions. Essentially, they added in a way that the data set was infinite. They were generating them on demand, and they were able to achieve the state-of-the-art accuracy. And they were actually not even using convolutions. So this is an example of a thing you can do.
Were they using fully connected layers?
Yeah, they were using fully connected
How
layers.
many layers did they use?
I think 5.
5
Yeah, 5 fully connected layers. I think around 500 units, 500 to 1,000.
And what's the accuracy they achieved?
It was something like 40 errors. I think maybe. So I think Jan Likun has a page with all the results. So let's see. this. Okay, so this is the series sum. Actually, it may still be state of the art. So this is the architecture they used. They used the 6-layer neural network. Wow, it's actually bigger than I said. It's 2,000 hidden units, 2,000, 2,000, 1,500, 1,000, 510. And there is no convolutions. And it achieved only 35 errors.
Error rate, right? That's the error rate.
Yeah, so there's 10,000 examples, and 35 of them were misclassified.
To make sure I understand that, that'd be like those from 784. That's the dimensionality. That's the pixel number of pixels.
Yeah,
Right?
28 by 28.
And then it's a fully dense network to 2,500.
Yep.
What's the interpretation of that? Because, like, in my mind, you know, you've got a lot of redundancy if you're describing 784, you know, things into 2,500. Like, is there some value when your activation function is nonlinear in terms of how you span the space to have redundant representations?
Is there value to have redundant representation?
Like, I guess from an information theory standpoint, I'm thinking like you can fully describe those 784 things with 784 things. Like, clearly that's wrong. That it makes sense to expand the dimensionality, and I'm curious if there's any logic to like either how you would choose 2,500 or why it needs to grow from 784.
Oh, I see. I don't remember him explaining this in his paper. It seems more of an empirical thing that he tried. Oh, you're asking why do you need to go up in dimensionality?
Yeah, so like why do you
I
need
see.
to go up and how far up do you need to go? And why do you go? Yeah.
Well, you can think, suppose you had only a single layer. Suppose you had input, then you had a single layer, and then you had a linear classifier at the end. You have to increase the dimensionality because in the end, the final layer, it is only able to perform if the classes are linearly separable. So what happens is that you have to increase the dimensionality to allow this linear separability to happen. So that's the basic intuition. You're increasing dimensionality because it allows you to make the classes linearly separable.
Okay. And then any thoughts on the arc of like shooting up and then gradually decreasing?
Yeah. So one principle that's sometimes used is to have the constant number of floating point operations at each stage. I'm guessing that's not the case here. So for ImageNet design, that's one principle they used.
As you're averaging.
Yeah. So one of the architectures typically use the increased. So at each case, you start with a large number of spatial dimensions, but a small number of filters. And then as you're doing convolutions, your spatial dimensions decreases, but then you're having more filters. So you may have. So one principle for designing the ImageNet models is to keep the computational complexity of each layer the same. For this one, it may be purely an empirical observation. Okay, any more questions? Yeah, so that's actually kind of surprising that it's still the best. So there's the same guy also got 27 errors and 23 errors by just averaging a bunch of neural networks together. Oh, so here he actually moved to convolution and then he averaged a bunch of them together.
So you said Schmidt-Huber's team did this.
Yeah, so Sirisan is Schmidt-Huber's student.
Okay, but probably his name is
Sirisan.
follows Sirisan. Sirisan at all.
Yeah. There was at one point a paper which achieved 0 error on a NIST test set, but it didn't pass the peer review. But I was hoping it would because it would kind of put an end to this exercise. So the question was what to do if your training set and test set are different. Actually, you do the same thing as here. You basically make your task harder. So you increase your, instead of trying to fit the original data set, you add a bunch of distortions and you try to fit that. So the general philosophy, just make your task harder for training, and that will make make it better in generalization. So suggestion, adding dropout. So dropout is a kind of noise. Another example people sometimes use parameter noise. People sometimes use gradient noise. You compute gradient and then you just add some noise to your gradient estimate. People recently experimented with synthetic gradients where you compute some gradient but you use an incorrect rule for the gradient. And there's many different ways of getting an incorrect rule. And those things help generalization. And if you think about it, if you add those extra obstacles and despite them you still are able to fit your training data, then your test data will also be well fit. This is actually what makes neural network hard to debug. People say that bugs are a regularizer. So you can have a stochastic gradient descent and you have some bugs in it. It can make your test performance better, theoretically. Although in practice what happens, it can make your training error completely terrible. So bugs only help if you can fit the training data despite the bug, in which case your test error will be pretty good. Okay, so this graph is about training set of capacity. So this is, I'm not sure where this came from, but it seems to be some kind of a polynomial regression because it has a polynomial degree on this axis. And then it just shows what is the optimal capacity for each number of examples. Learning rate is probably the most important parameter. So what happens is if you increase, one of the interesting things is that the bigger your learning rate is, higher learning rate actually improves your final accuracy, or it completely makes things explode. So a practical approach is you want to make learning rate as high as possible until it just stops helping. So there's sort of, you want to be just on the edge of chaos, where if you increase your learning rate just a little bit more, things will stop learning. But at that point, that's a good rate. One possible explanation of this phenomenon is there might be a connection in this between simulated annealing. So simulated annealing, it comes from physics, and the idea is you have some energy landscape, and then when you're trying to find the minimum, you first have this high energy particle that has high energy and it's able to jump between minimums, and then gradually, as you cool it down, it gets trapped by one of these, and it gets minimizes to this point. And there's actually some theorems. If you have to do a global non-convex optimization, you can actually provably find the global optimum by using simulated annealing. However, the scheduling, the temperature schedule is pretty slow, so it's not usable in practice. But you can think of deep learning following the same procedure. If you have a high learning rate, essentially you're jumping between many different minimum, and eventually it settles into the best one. So in the book, he has a table reasoning about hyperparameters. They seem to be mostly common sense. So if you have more hidden units, your capacity is increased. So if you're thinking about increasing the capacity of your model, you can increase the number of hidden units, you can increase the number of layers, you can increase the filter size of your convolutional layers. So whatever increases the number of your parameters typically increases the capacity of your model. There is also an issue of regularization. Things that make it harder to fit the training set, you can think of them as decreasing the capacity of your model. But maybe a more correct way of thinking about them is things that make it harder to fit your training set are the things that improve generalization. And then there's a section on hyperparameter search. In Google, there were several efforts to do an automatic hyperparameter search selection. Essentially, every year there would be an effort to do this. And honestly, I haven't seen much success.
But is randomized search is preferred over grid search?
Yes, randomized search is better.
Like the right one is the randomized one.
Yeah. So one problem with hyperparameter search, you have to provide some parameters to your search procedure. So your hyperparameter search procedure has hyperparameters of its own. So usually you have to have a good guess where to look before giving it to your hyperparameter search method. And often I found that in tasks where training takes for a long time, it's easier to just try a few things yourself and set it as a new baseline and continue from there.
So during this hyperparameter search, do you sample from the training set to figure out what is the best hyperparameter to train on? I mean, you won't be.
So traditional hyperparameter search methods, you give it a set of hyperparameters to experiment with and the range of values for each hyperparameter, and the procedure will train with those hyperparameters and evaluate on a validation set. And that's the point of information that the hyperparameter search method uses. So there's actually quite a bit of research in the good hyperparameter search methods. People use Gaussian decision processes. And if you have a task where you tried many things and you want to push it, those few extra percentage of accuracy, that's an area where hyperparameter search can be useful to get those few extra degrees.
Like, do you have any recommendation? For example, I have a huge training set, but it takes too much time to run it on every hyperparameter I want to try. So how much percentage of training set should I try for one search?
Right. So the problem is that I haven't seen them to be very useful. So it's hard for me to say. You could try to have some subset which just runs in reasonable time. If you have a feeling that you want to try 100 different settings of hyperparameters, find a good result, you just make it small enough so that those 100 settings are run through before you run out of time. Any questions?
Just really quick on the training and test error. Do you, in practice, use the actual test error, or are you using like cross-validation?
So for the application with the house numbers, we collected a set of labels and we withheld some for later. So we tuned and experimented on our framework on those examples. And the thing is, in real-life application, your ultimate test is how it performs well in practice. So typically you try to tune it to work as well as possible on the test you have, and then you just ship it and then see how well it works. Sometimes it's useful to set aside an extra test set, so you have some evaluation you do on your test set, and then at the end of the procedure, you try it on this extra test set as a sanity check. However, the thing is, if you have large enough data set, it's not that important. So for the house numbers, we actually, if we looked at the training errors and the test errors, they're essentially identical. So whenever we decreased our training error, we decreased our test error. So that was not really an issue. So in that example, we had maybe 50 million training examples. So at some point when you have, I would say more than 20 million examples, then the overfitting disappears if it's the size in this kind of domain. Okay, so let me just run quickly through this chapter to make sure I didn't miss anything. Unless there are questions? No questions. Okay. Okay, so methodology. So what do you need to do? So there's 3 things. You first need to decide the error metric to optimize, make an end-to-end pipeline, and then you make incremental changes. The one extra thing this book talks about, you typically instrument your system. So instrumenting the system, the most common ones is you just want to look at the errors. So if you're using TensorFlow, your tensor board already shows you examples of things. Let's see. So one issue when designing your cost, sometimes it's more costly to make one mistake than another. So one example is the Google photo classification app. At one point, we got a call from senior VP, and he said there was a big problem, and it turned out that the Google Photos app classified some black guy as a gorilla in his photos collection, and he made a post about it, and it went viral. So that's an example of misclassification, which is very costly. On the other hand, the Google Photos often classified children as dogs, but nobody ever complained about it. So the solution to this was just to take out all gorillas, monkeys, and simians out of the label. So essentially, you're trading one error to another. Now all gorillas are misclassified, but that's a low-cost error. So when you're designing your metric, you want to sometimes think about these things. So another problem of dealing with accuracy is when you're detecting rare events, it's easy to get very high accuracy by a very simple classifier. So for instance, if you're trying to find a rare disease, the classifier that just says healthy is going to be correct most of the time. One application this came up with once is trying to train a classifier which would take each pixel and then would classify if it's a particular class. So for instance, there's 1,000 classes, maybe like dog, cat, and then each classifier, this would be a dog classifier. And then it would just say, is this dog? And then for this pixel, it would say, is this dog, etc. So vast majority of pixels are not dogs. And what would happen is we would call it the classifier going blind. When we optimize for the accuracy, it would just learn to classify no for all examples, and it would just get stuck there. And the solution for this situation is to make those errors more costly. So whenever it would actually be a dog and it would say no, you would just have a cost multiplied by 10,000. And if you make it high enough, eventually it doesn't go blind.
It's kind of like boosting algorithm.
Oh yeah?
Basically, you weight your samples according to the importance.
Right. I guess here you fix this weight as opposed to changing it. But yeah, it's similar. Talked about precision and recall. The thing about precision and recall, if you have a object detector with a neural network, it outputs a score, and then you can choose the threshold. And if you adjust the threshold, essentially you get a different answer. So what you do is you get some kind of precision recall curve like this. And if you fix your score, you get a single point on this curve. So you can either report precision recall at this point, we can recall this F ratio. Here, this thing doesn't highlight. Or you can compute the area under the curve. So area under the curve is sort of independent of this threshold. So you need to get an end-to-end system. Regularization. Regularization is useful even if you don't have overfitting. Regularization seems to somehow help training. So it's a general rule of thumb to always have a little bit of L2 regularization, even if you don't have even if you don't have an overfitting problem. He talks about using unsupervised learning. I guess it can be helpful sometimes, but I haven't used it much. So there's also always a question, should you spend more effort gathering more data or improving the algorithm? And so far, the common wisdom is if you can double your training set or multiply it by a magnitude of 10, that's generally going to give you a better performance boost than spending a month designing a new algorithm. So learning rate, so if you're tuning hyperparameters, the two things you really tune is the size of your network, which means the number of layers and the width of each layer. And the second thing is the learning rate. And the learning rate is the most important parameter. One of the developers in the Google Brain team had a t-shirt which said, lower your learning rate. Because people would complain and they would say, my neural network, it explodes. It has infinities, it has NNs, not a number. And the answer has always been lower your learning rate. However, the problem is, if you lower the learning rate, eventually you solve the numerical issues, such as getting infinities or not a number, but your accuracy also suffers. Okay, so in some debugging strategies, one example he gives, you can have an incorrect gradient update rule, and your model can still work. So here is the example. You have a bias, and at each step, you just decrease your bias by some number. But if your model is big enough, the model can compensate by increasing the magnitude of the weights. So you will never discover that you have a bug in this SGD. So this is a general issue of stochastic gradient descent being resilient to bugs. So another thing is you have to visualize the mistakes, especially the worst mistakes, meaning the mistakes where the model is very confident, but also very wrong. Later he talks about them, yeah.
Yeah, so when you see those kinds of mistakes, what do you look for and what's your process?
So ideally, you look at this mistake and you see that it's basically incorrectly preprocessed. So the examples we discovered in the Street View house number, we saw that the worst mistakes is actually where the model was correct, so the labels were wrong. And hopefully that's the situation. If that's not the case, then you're dealing with the same situation as here. You have to increase your model capacity or increase regularization and hope that the mistakes go away. But that's the technique that's really useful for finding problems in your data pipeline. Later he talks about checking the gradient. So if you're not using an existing framework, you're implementing the gradient yourself. There's this technique called finite differences, and you can use it to check that your gradient calculation is correct. Okay.
Do you guys have any questions about the chapter? We covered everything. I think we were actually following chapter pretty closely for once.
Well, the slides were actually really good.
Thank you. So we finished a little early. We always go to town hall for some beer. It's just like a block and a half away from here. If you guys want to join, come with us. And next week, same place, same time, Ian Goodfellow for chapter 12.